Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're going to start another little mini-series, 6-part mini-series on randomized complete blocks ANOVA. In this first one, we're going to deal with model development. Now, we have A treatments and B blocks. Every treatment appears within every block. That's what when we say complete. So complete blocks means within a block, every treatment is seen. Now the order in which the different treatments are randomized within a block are randomized, and I'll illustrate that in a second. This is, and I double underline is, a restriction on randomization. And if you use a randomized block design, but then analyze it with a completely randomized design, I don't think you're doing justice, because you need to account for this restriction on the randomization. This is going to mirror the repeated measures one-way fixed effects ANOVA. That's the preceding mini-series in this playlist. And we're going to point to a lot of the theory and the proofs. We're just going to state them in this little mini-series and point back in this one for if you want to see a proof of the derivation. Now the model in scalar form is this. It's yij equals mu plus tau I plus beta j plus epsilon ij. I goes from 1 to A. We have A treatments, and j goes from 1 to B because there's B blocks. Now yij is the response for the ith treatment within block J. The mu and the taus and the betas are fixed unknown parameters, and this is initially. We'll change it up a little bit as we proceed through this little mini series. Epsilon ij, or IID normal, mean zero, constant variance sigma squared, and this is for all ij. Now the general layout for this, and let's ignore this for a second. If we have treatments 1 through A down the side and blocks 1 through B across the top. Now these subjects, or these units, these, whatever you want to call them, you randomize them within a block. And then here, these, I do a lot of clinical trials, so this is, I think of them as subjects. So these subjects are randomized within that block. But please note that once the first A-1 observations are set or picked, this last one is deterministic, and so it is a restriction on the randomization. Don't kid yourself. Now if a block, so up here, is a subject, this is the previous mini-series that I called Repeated Measures One-Way Fixed Effects ANOVA. Now blocks can be considered fixed or random. However, in this little mini-series, blocks are going to be fixed. Previous series, blocks were random. In this repeated measures one-way fixed effects ANOVA. So if you want to get a little taste of that, I would watch the previous mini-series. Now for the matrix form, or the layout for matrix, it's y equals x beta plus epsilon. That's the general form. Y is an AB by 1 vector. X is an AB by A plus B plus 1 matrix. Beta is an A plus B plus 1 plus by 1 vector. And the epsilons are IID with a mean vector 0 and constant variance sigma squared. Covariances are 0. Now in the Y vector, the response vector, we order them by treatment and then block. So we take the first B observations. These all correspond to treatment 1. And then we order them by block, 1, 2, 3, 4, 5 to B. And then the next group are all correspond to treatment 2. And then they're ordered within block. And of course, we continue until the 8th treatment. And then we order them within block. So x beta is this form. We'll do beta first. Beta is mu plus tau 1 through tau A, beta 1 through beta B. And here, this vector of 1s corresponds to mu. So that way when this multiplication takes place, the mu is always picked off. Now the next group, there's A columns here, and this corresponds to treatment 1, and it's a length of B. That way when you do this vector, this product, matrix product, it's always picking off tau 1. And then this is the diagonal. So on the first one it picks off beta 1, and then the second one it picks off beta 2, and then goes all the way down to beta B. Right? And then it continues, and the last group, of course, associated with treatment A, this one, and then this is diagonal again. That way the math ends up correct. Now, commonly we just call this column of 1s. This here is the column space associated with treatment, so we call it x tau. This is x beta, since this is associated with the blocks. Of course, the mu parameter, but then we just think of this as a vector of taus, and this is a vector of betas. And then when we do that multiplication, we get this. So this is how it is usually seen. Remember, this is only x beta. So when you write out the model, of course, there'd be an error term associated with it. But this is the design matrix times the parameters. Now, in the next 5 videos, we're going to look at the projection matrices and the column spaces associated with the design matrix. We're going to look at the sums of squares, estimability and contrast, and then we're going to talk about random treatment effects within the complete block design, and then part 6 will illustrate this with the R software. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.